Machine learning models can be built by plotting points in space and optimizing a function based off of those points. For example, I can plot every person in the United States in a three-dimensional space: age, geographic location, and yearly salary. And then I can draw a function that minimizes the distance between my function and each of those data points. Once I define that function, you can give me your age and a geographic location, and I can predict your salary. Plotting these points in space is called embedding. By embedding a rich data set and then experimenting with different functions, we can build a model that makes predictions based on those data sets. Yufeng Guo is a developer advocate at Google working on CloudML. In this show, we described two separate examples for preparing data, embedding the data points, and iterating on the function in order to train the model. In a future episode, Yufeng will discuss CloudML and more advanced concepts of machine learning. Unfortunately, we were time constrained in this episode, but it's really elegant. It actually turned out to be a really elegant episode where we discussed this embedding process and this simple model training process that had been very confusing to me for a long time. And so hopefully this key aspect of software engineering will be made more clear by this episode. I hope you like it. Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily. Yufeng Guo is a developer advocate working at Google on CloudML. Yufeng, welcome to Software Engineering Daily.
Thanks, Jeff. Really happy to be here.
In today's episode, I'd like to talk through some elements of machine learning and then talk about how Google is building some tooling for that in the cloud. Let's start with a running example that you use in many of your talks, which is an app that predicts what users want to eat given a phrase. So for example, a user could say American food, and maybe the user should get a hamburger. Maybe the user should get a steak. We don't really know. It's just an abstract query, but the idea is that we can use machine learning to figure out how to answer a query for a general type of food with a specific response. So I should be able to say salty snack, and it could recommend potato chips. I could say dessert, and it will recommend a milkshake. And it knows who I am. It'll recommend a good milkshake based on that. You've talked through that example in so many of your presentations, and I think it's worth going over as a nice example to the listeners. So let's first talk through the most naive version of that food recommendation app. What do you need in order to build this recommendation system for foods?
Well, the first version I talked about is perhaps too naive. It's literally just a string matching system. So it's, if you say fried rice, it will just look up in its catalog of foods available and pick one at random that has the words fried and rice. And that might get you like some esoteric dish like fried rice pudding. Or it might get you something like actual fried rice, chicken fried rice or something like that. So I assume we're talking about the first machine learning option here.
Yeah, absolutely.
Yeah, so basically I kind of talked through the string matching example. It's kind of a joke, and then that doesn't go so well. So the first thing you do is you try out just a simple linear model. So that's just a linear classifier, one that we kind of see, we've seen used, to a great effect for many, decades now. And one that now kind of deep learning and stuff is coming in and improving upon that. But this first linear model helps just categorize and memorize really what a given user's preferences are and memorize these associations between, say, salty food and potato chips.
To build this recommendation system, we might want to use what is called an embedding space to map different elements. So what is an embedding space?
Yeah, so an embedding space is intended to be a way to represent the relationships between, in our case, the objects or items on our food menu, so to speak. And what it does for us that's better than, say, just having a raw list, literally just, say, an array of all your different food items, just all in a row, all your ducks in a row, is that you can get this kind of almost a spatial relationship between what is similar and what is more different. So the further apart something is, the more different it might be. We see this a lot with text processing, where similar words are clumped together and words that mean things that are very different from each other are further apart.
Mm-hmm. And we did a show about Tyvek, which is an embedding space for words, essentially. The idea with Tyvek is if you take all these words and you plot them on a geometric space, just all the words in a corpus, you would have words where they would have these relationships. For example, king would have a geometric relationship in this n-dimensional space to queen, and it would have the same geometric relationship that male would to female. And if that sounds really confusing, go listen to that Tyvek episode. But basically the idea is that given enough data, you can use these fairly naive ways of plotting relationships between words, and you can get a really good semantic understanding for what people mean when they say one thing, and you're looking for synonyms for what they might be meaning. How would building an embedding space for foods work? How would you do that?
So in, like you said in my talks and stuff, the particular example we go through using TensorFlow is that basically it's just a call, it's just an argument in our construction of the model. We pick a dimensionality for the embedding space and we just say like 8 or 16. And there's not much more literal work involved, in terms of programming that. But conceptually, what's happening is all these items are kind of just being scattered in this, n-dimensional space, let's say 8. And as the model kind of trains on the training data, it learns these relationships between different things, and it basically starts moving all the items relative to each other, so that as you could think of it like if you had a space and you were getting all these foods streamed into you, and you're saying, okay, strawberry goes here, and then you get like pineapple, and you're like, okay, that's a fruit, let me put it near the strawberries, and you get one that's like beef steak. It's like, okay, that's really different, so I'm going to stick it over here. And a cake comes in, bread comes in, and you put them in different places. And as things come in, you are allowed to move them from their original positions. So then you can make adjustments, say, oh, I messed that up. I need this to actually be between these two other items. So let me just shift that all the way over here. And that's kind of how the embedding space gets built up over time as the training happens.
Mm-hmm. So let's say we have a bunch of foods in a text file. And we have, I don't know, maybe they have some fields that describe the different foods. How are we turning these fields into numerical dimensions? Because we need to plot these foods in an n-dimensional space. And what would some of those dimensions be?
Well, that's a really good kind of phrasing for that, Jeff. The actual dimensions themselves are not necessarily always interpretable, which leads to various notes around interpretability of machine learning models and like. But the parameters you have, right? And usually when you're training the system, you also have some kind of goal that you're kind of training it toward. But the various parameters, let's see, how can we describe this? Characterizing things over audio is always tricky, right?
Of course.
Yeah, so you can take each column of your data, right? Each of these features, like how salty is it? How soft is it? How crunchy, yes or no? And turn them into kind of numerical features rather than string categorical ones. So you can say the hardness of a piece of hard to soft, right? So like 1 through 10 or 1 through 100, depending on your level of granularity you want. Things that are just yes or no can be zeros and ones. So once they're converted into numbers, then the model can then take that and kind of build the mathematical relationships, because with just words, there's no kind of numerical relationship. They can't add and subtract words, but once they're turned into numbers, they can be worked with not only more quickly on a machine, right, that's thinking in numbers, but also it becomes a tractable problem.
And so let's say we've got all of these different foods that have been plotted in terms of their crunchiness and their softness and their savoriness. And I'm getting hungry just talking about this. Okay, we have this data that has the crunchiness and the saltiness and so on. And so we can use those to plot these foods in an n-dimensional space where you've got every food is plotted in terms of saltiness and savoriness and so on, plotted in an n-dimensional space. What are we doing with that embedding space in order to build a querying engine?
So once we have this in space, and I want to emphasize that we're not plotting this manually. We're not literally taking each of our potentially thousands or millions of food items and trying to position them by hand into a place. This is done during the training process automatically by the machine learning process. And so when you have, when you're doing the training, and let's say in our example, we have labeled data that we say people prefer blah when they ask for salty food or crunchy food, they get potato chips or something. And so with that data, you can then iteratively train your model. So when your model has the embedding stuff, but it also has, whether it's a linear network or a deep network, the representation of this embedding space is simply, it's just a way for the model to kind of hold the data in some form that's not just a raw list of values. And by having it in an embedding space, it allows it to understand more, like we talked about before, between like king and queen. It learns these relationships, right, where it can almost understand, quote unquote. And when I say understand, I guess it really is that we looked at the model, humans, and said, oh, wow, look, it like created this mathematical relationship. So we kind of say it understands, but it doesn't understand like in the brain sense of it. So yeah, does that sort of answer your question?
So it explains the relationships between them. So we've plotted these relationships. What exactly is going to happen then once we have those relationships in geometric space when I ask a question or when I say something like American food?
Right. So this is now we're kind of getting to the other side of machine learning, right? So I always think of machine learning as the great divide, quote unquote, of training and prediction. Having this data or examples and answering questions. And the answering questions side is what makes machine learning useful, this making predictions. And so you're absolutely right that when you then ask for American food or ask for seafood, one way to do it, right, would be, and conventionally you could look at just basically saying, in the embedding space, you have these clusters of different types of food groupings, if you will. So if you say American food, you have a bunch of American food like in your embedding space. You can think of it like in space. There are all these different American foods, and it would quote unquote just pick one. But with a trained model, it has also learned your individual preferences. So there's kind of that additional nuance wherein it can pick one based on your preferences beyond just saying, okay, I'm just going to pick a random item off of the menu of lots and lots of American foods out there. And there may be, and probably should be, other criteria involved as well when you are training the model. Things like time of day, what did you have before, where you're located, things like that.
DigitalOcean Spaces gives you simple object storage with a beautiful user interface. You need an easy way to host objects like images and videos. Your users need to upload objects like PDFs and music files. DigitalOcean built Spaces because every application uses object storage. Spaces simplifies object storage with automatic scalability, reliability, and low cost. But the user interface takes it over the top. I've built a lot of web applications, and I always use some kind of object storage. The other object storage dashboards that I've used are confusing, they're painful, and they feel like they were built 10 years ago. DigitalOcean Spaces is modern object storage with a modern UI that you will love to use. It's like the UI for Dropbox, but with the pricing of a raw object storage. I almost want to use it like a consumer product. To try DigitalOcean Spaces, go to do.co/sedaily and get 2 months of Spaces plus a $10 credit to use on any other DigitalOcean products. You get this credit even if you have been with DigitalOcean for a while. You can spend it on Spaces or you can spend it on anything else in DigitalOcean, and it's a nice added bonus just for trying out Spaces. The pricing is simple. $5 per month, which includes 250 gigabytes of storage and 1 terabyte of outbound bandwidth. There are no costs per request, and additional storage is priced at the lowest rate available, just a cent per gigabyte transferred and 2 cents per gigabyte stored. There won't be any surprises on your bill. DigitalOcean simplifies the cloud. They look for every opportunity to remove friction from a developer's experience. I'm already using DigitalOcean Spaces to host music and video files for a product that I'm building, and I love it. I think you will too. Check it out at do.co/sedaily and get that free $10 credit in addition to 2 months of Spaces for free. That's do.co/sedaily. Let's jump to another example. Let's go to the example that you give around census data, and this will motivate further how to build a model, and we'll talk through building a model. So given a census data set with things like marital status and age and education, these numerical fields, the question is, can we build a model that predicts whether each person has $50,000 or more a year in income? And so all of this data is labeled. Like, let's say we know the salaries of all the people. So we've got marital status, age, education. We've also got their salary. But we would like to be able to predict without labels. We would like to have a situation where even with unlabeled data, where we just have marital status and age and education, we can predict what their income is, whether they produce $50,000 a year in income or not. So much of the work involved in training this model is in preparing the data for input. So let's say we've got this giant CSV of data. We've got a data set, and we want to prepare the model for the training. Describe what happens in this input function. This is sometimes described as data cleaning or data preparation. What goes on if we just have this giant CSV of labeled data?
Absolutely. So this data cleaning or setting up your data for machine learning definitely ends up being the bulk of the work. You see it in the code, just like most of the code is setting it up, and then running the machine learning is just like the couple lines at the bottom. And when we first start out, let's say in our data set, and in the example that we're talking about, even the labels are not 0 or 1. They're actually just the string field that is like, it says greater than 50K or less than 50K. So it's literally the greater than sign and then 50K. Or less than equal sign 50K. And so we need to process that into a 0 or 1, process them into classes. And if we had a situation where there was more than one class, let's say we wanted to segment it into 3 different buckets of income instead of just above or below 50, then you would classify those as 0, 1, or 2. So giving these indexes, typically 0-based indexes. Then you would also perhaps want to do some transformations on some of your other features, some of your other columns. For example, you might look at the age column, for instance, and realize that we don't need to have literally the fine grainness of age of every single age number, like 24, 25, 26, all the way up, and that it would be more useful to have age buckets, age groupings, because we care about the 18 to 24 age range, what kind of income do they tend to make? And that can oftentimes lead to more useful insights than being so granular that the noise starts really affecting your model. So you can bucketize your data in that way. And that converts your data, that particular column, from being continuous, right? Age is like just a continuous value, to being categorical, where you just have a handful of different categories. And oftentimes the question comes up around even something like age, where it's a value that's like sort of both. You could look at it both ways. You could say, well, age is just is a number, so it's continuous. But you could also say, well, there's only probably no more than around 100 different possible values, so that's kind of categorical too. So at their limits, they tend to blur a little bit. And typically when we think of categorical, we're referring to generally on the smaller side of things, though that has been pushed, right? And then continuous, on the far reaches of it, it's like just truly continuous numbers, like rational numbers. It can be any decimal number, but oftentimes you can use bucketization or things like that, techniques to turn a continuous column or feature into a categorical one. And having those kinds of operations, and you can also do feature crosses. So let's say you had a column of education and a column for occupation. And so you might, look at your data and you say, I suspect there might be some correlation between, the highest degree someone earned and what occupation they're in to help predict income, right? That's not entirely unreasonable, but, you don't want to do like the statistical analysis to figure out the relationship between these two columns. You can just make a third feature called, the occupation crossed with education. And so it's asking the question of, given that someone got to this level of education and they work in some field, what will they be above or below $50,000 in annual income? And so having these additional parameters can help sort of round out your model, especially in situations where maybe you don't have as many columns. This allows you to get some more columns out of your data and allows your model to kind of take advantage potentially of some other ways of looking at your data, because the model itself doesn't understand. Let's go back to the age example. It doesn't know that you're okay with bucketizing the age column. So that's why it can be useful to kind of provide that up front, and that'll kind of make the model oftentimes more accurate, and it can also make it easier or faster to train. Things will converge better.
Yeah. So Yufeng, I'm obviously not an expert in machine learning. So tell me if I'm wrong about what we're doing here. We are plotting all of these data points, these rows, across each of the different columns. We're defining values for each of these columns because some of them might be kind of weird. They've got a text input, and you need to figure out what value would be assigned to a text input, numerical value, because you're plotting them in Cartesian space. So you're plotting them on a numerical space. And the reason that you're plotting them in this n-dimensional space is because you're going to use these plotted points to describe as data points to interpolate a function that goes through as many of these data points as possible, and with that function, you will be able to accept new data points and see where those would plot given the function that you have defined over the training data points. And because there are many different functions that you could describe that would go through these data points, that's what the whole training process is about. You're saying, how am I going to train? What kind of function do I want? And what do I want to optimize for? Because maybe under certain circumstances, your function would pass through 50% of the data points. In other functions, it would pass through 30% of the data points, but you would be emphasizing some particular aspects of those data. So maybe you're more likely to cross through the salty regions in the food example because you think that people happen to always want to optimize for salty foods. Am I describing this process that we're working towards accurately?
Roughly, yeah. And it sounds like you must have a very particular math background to be bringing up all these functions. So the machine learning models, especially when it comes to kind of the more recent neural networks and things like that, and even linear models, can often be thought of as trying to approximate a given function, right? And there's a couple of nuances there. I wouldn't necessarily say that we're trying to have the function pass through as many points as possible. That's generally not the kind of objective or goal of the training, but rather that if you were to measure the distance away from all the different data points, how far are they from the function that you have chosen to kind of plot? And we summed up all those kind of distances, how far off we are, and like, let's say average them or something, then we want to try to minimize that value. So we try to get as close as all the things as possible.
The loss.
Exactly. And that's oftentimes referred to as loss. Sometimes it's called error. And the danger here is where when you have data that's maybe a little bit noisier and things like that, if you actually create a function that passes through every single data point, it's just going to be going all over the place, right? If you ever, had a data set in Excel and instead of having the curve plot through, a nice fitted curve, but to actually just draw set line segments between every single point, it's just this jagged, all over the place value. And if you were to just interpolate, you might have, what used to be a trend line that just goes nice up smoothly, but now it's kind of up and down, up and down, up and down. And for any given point, it might be going down or it might be going up, and you just get all sorts of wacky values out of that.
Okay, so let's say we've plotted let's say we had these billion data points of people in a census data set where we got marital status, age, education, and we also had the labeled data, whether they had $50,000 in income or not. And now we get some new, let's say we wanted to iterate over, we want to do machine learning. We've got these example points plotted. We want to do machine learning. Describe what happens in each training step. How does training work once we have these examples plotted?
Yeah, so what we take then is we take each training step. So we're going to train this system iteratively, as you mentioned. And at each training step, we're going to grab a batch of our training data. So instead of trying to determine how to adjust our function, so the goal here is each step we're going to adjust our function slightly, hopefully to make it so that the loss is a little bit lower than it was in the last step. So that's kind of the overarching goal, is how can we iteratively adjust the loss such that it decreases with each training kind of step. Then we say, okay, ideally, we would be able to figure out how to adjust our function by looking at our entire data set. We would take our, in our case, let's say 1 billion rows of data, and we would figure out how that, by running it through the existing model, right? That's like, let's say step 1, we would figure out, okay, we need to adjust the function in these ways to make the loss a little bit lower. And then this next step, step 2, right, would be you would take the same billion training data and you would come back and you would adjust the function and make the loss a little bit lower again. But there's a practical limitation here in that taking 1 billion data points just to do one training step, because you might be doing thousands of training steps, is the reality here. And computing 1 billion values and then adjusting the function just to get a little bit of change, oftentimes it's not worth it, right? So what you do instead is you take a representative batch of the training data. So let's say you just take 1,000 data points. You just take a random sample of 1,000 data points. And the idea here is that those 1,000 would be representative of the entire data set. And so we say, the 1,000 is good enough, and we'll use that to adjust our function slightly. And then we'll check to see what our error is, and then we say, okay, we did a decent job. Let's grab another representative 1,000, a different 1,000, and adjust the function against that. And so by doing it this way, it becomes a much more practical and kind of computationally tractable problem, where you can actually train for many, many training steps, thousands of training steps, without having each step take minutes or hours at a time. Right? Now you can do 1,000 training steps in just a couple minutes or something.
Okay, that's great. Can you define the term hyperparameter tuning?
Yeah, so as we go through the process of training, there's a lot of parameters that we end up sometimes arbitrarily picking. Earlier when we talked about embedding spaces, I said, you can just do 8 dimensions, 16 dimensions, however many you want. Or just now when we were talking about the batches that we do in training, I just said we grab 1,000, but what if we grab 2,000? What if we grab 500? These parameters are typically referred to as hyperparameters in our model, because the actual parameters are is the function, is what defines the function of the model. So hyperparameters, throw a hyper in front of anything and it becomes fancier, right? And so you can adjust these values and they will affect your training, right? If you embed your data in 8-dimensional space versus 16-dimensional space, depending on the complexity of the data, that can have a real material difference. And sometimes the batch size, or sometimes when you're training, you'll go through your entire training set multiple times and loop through it a lot. And that can affect how strongly the function is kind of fitted to the data set, whether it's kind of just a loose, smooth fit, or does it become more tightly bound to all the existing training data. Then that kind of gets into overfitting and stuff. And we don't have to necessarily go that way. But that's kind of what hyperparameter tuning is. It's to improve, and the whole purpose of it is to improve the final outcome, right? Whatever objective function you have, where you're trying to improve some accuracy or you're trying to improve decrease the loss. Doing hyperparameter tuning means you're just running through the training cycle with different training parameters, so to speak, batch size, the dimensionality, and even which features you start tinkering with, right? Bucketizing which feature, crossing which features together. Those are also decisions that you make that will impact the outcome of the training, and you can make those adjustments to end up with different outcomes. So that's kind of what hyperparameter tuning. You can explore this kind of parameter space, if you will.
The octopus, a sea creature known for its intelligence and flexibility. Octopus Deploy, a friendly deployment automation tool for deploying applications like .NET apps, Java apps, and more. Ask any developer and they'll tell you that it's never fun pushing code at 5 p.m. on a Friday and then crossing your fingers hoping for the best. We've all been there. We've all done that. And that's where Octopus Deploy comes into the picture. Octopus Deploy is a friendly deployment automation tool, taking over where your build or CI server ends. Use Octopus to promote releases on-prem or to the cloud. Octopus integrates with your existing build pipeline, TFS and VSTS, Bamboo, TeamCity, and Jenkins. It integrates with AWS, Azure, and on-prem environments. You can reliably and repeatedly deploy your .NET and Java apps and more. If you can package it, Octopus can deploy it. It's quick and easy to install, and you can just go to octopus.com to trial Octopus free for 45 days. That's octopus.com, octopus.com. So we're optimizing for, so we've got this set of data points that are plotted in space. We're trying to figure out what is the best function that we're going to build across this space, and that in changing that function over time, we're optimizing for something. Maybe we're optimizing for accuracy. Maybe we're optimizing for the lowest loss. We're trying to minimize loss. Can you contrast those two things that we could be optimizing for and how those would change our model tuning over iteration? And by the way, the things that we're optimizing are the hyperparameters, right? Those are like basically the knobs that we're tuning over time to create this model.
Yeah, that's a great way of putting it. They're the knobs that we kind of can turn in our model. And in terms of accuracy and loss, the notable difference here is that accuracy is, well, it's exactly what it sounds like. So if you had 100 different data points and you got 99 of them correct and one of them wrong, you have a 99% accuracy. On the other hand, loss can be thought of as a little more nuanced, because with accuracy, you don't really capture how wrong you were. In some models, it's not just above or below a certain threshold, right? It might be you need to predict which one of these 30 categories something falls in. Or you might need to predict how or you may need to predict a real value, like a number needs to come out. And so measuring accuracy may not be as meaningful there, because you might not be able to even hit a number right on the head, especially if it's like, oh, the goal that you're supposed to hit is 37.2 and you predicted 37.1, so you're wrong. But actually you were quite close. And so loss is a little bit more nuanced and can capture the distance, if you will, from what you predict versus what the true value is. And that is often, like, in terms of choosing whether you want to use loss or accuracy as your metric for thinking about how well your model is doing, it comes down to your particular use case. So, like, using the examples that I gave there kind of is one way to think about that. The other aspect of it is that we talked a lot about the training and the training data so far. And strictly speaking, that you would also actually want to cut off a piece of your existing data set and hide it away and never show your model that data. And we'll use that for, it's called either validation, some people say evaluation, or your test data. Basically, it's you never show your model this data so that you can then later present this data to your fully trained model as a way to evaluate how it did. How did the training go? Because if you train your data on these 1,000 data points and then just present those same 1,000 data points to your model could very easily get away with just memorizing those 1,000 data points, and then it wouldn't be able to kind of generalize well to more real-world data that comes along down the road. So you have this evaluation data set that's kind of representative of all the other ones, but isn't exactly the same. And we also know the quote-unquote correct answers to those values. And so we show the model that, and that's kind of the evaluation step. And that's what we use to evaluate accuracy or loss or whatever it is. That's our metric for figuring out how did our training go? Mm-hmm. How well did we do?
Okay, I think I understand things pretty well. But we're talking about deep learning too. And tell me, we haven't really said the word layer at all in this conversation. So
yeah, somehow we managed to find away from that. Yeah,
we've talked about this fairly simple process of, relatively speaking, of plotting a bunch of data points, drawing a function through those data points, and then testing that function against new data and tuning it over time to optimize for accuracy or to minimize loss. Where does the layer conversation fit in? Where does deep learning fit into this?
Yeah, so everything we've talked about, a lot of what we talked about so far is just more general machine learning concepts, and it is almost agnostic to what model you're working with. Deep learning is one particular way to do machine learning, and basically, at the simplest level, you can think of it as you're taking classic linear regression and stacking a bunch of basically layers of linear regression. So we say we're going to use a linear classifier or regressor and do one, but then we're going to take the result of that and just not actually use it as our answer, but instead feed it into yet another layer, quote unquote, of linear regressions. And we'll do that a couple of times. And so you have these kind of hidden layers, if you will, before you reach your true output that you're using to predict against your training data. So you have this kind of a lattice structure or webbed structure. It's typically, each layer has typically a different number of nodes, if you will, or neurons, as it often gets called. But the resulting structure kind of sometimes looks like a river delta almost, where all these rivers are converging, right? And then there's one outlet, like if you look at a satellite photo of the Nile, for instance. And so then the reason you want to use these layers and why would they be useful is kind of the natural next question, right? And what makes it better than, or oftentimes I should say, sometimes better than linear regression. If you have really clean data, that's not always the case. But with deep learning, it generalizes better because between each layer, there's what's called an activation function. And the activation function acts as a way to introduce a non-linearity to the model. So this means that while before we were only able to learn linear relationships, now we can stack these basically stack these linear models on top of each other. And you at first would say, well, that's still linear, right? The sum of a bunch of linear functions is still a linear function. And what we do then is we say, aha, we'll add in a little bit of a non-linearity in between each one. Traditionally, it was a sigmoid. Nowadays, a lot of them use what's called a rectified linear unit, which is literally just a horizontal line from negative infinity to 0, and then at 0, it's just the 45-degree, y equals x line that just goes straight up. Oh, not straight up, but diagonally. And that is that kink in the function, so to speak, right at 0, 0, is enough of a nonlinearity for the network then to adjust its kind of parameters such that it kind of utilizes that, right? Because that function, what it's going to do is it's going to wipe out any negative values. So all the outputs from the previous layer going into the next one, it's going to filter out all the negative ones, and it's going to map all the positive ones directly forward because it's just y equals x. And so by shifting how at each layer, it can shift its parameters to cause, which aspects to fall into the negative half versus the positive half. And if you have a bunch of different layers, it can do that repeatedly, and that can basically act as a gating function, so to speak, between the layers and introduce those nonlinearities and produce highly complex functions to fit any data set, given a large enough network.
Okay, well, so I think we've given a really good explanation for how to train models. And, unfortunately, we're up against time, so we can't go super deep into CloudML like I wanted to, so maybe we should do another show in the future. But let's talk a little bit about that. Let's talk about deploying these models. Let's say whether we've created this food recommendation model or this census data classifier. How are we deploying these to the cloud? And maybe you could tell me some about what Google has built with CloudML.
Sure. So with Google's CloudML engine, it's basically a managed service for running your Python TensorFlow code in the cloud at scale. So this is really, it really comes in handy when you have a really big data set and also really big compute needs, which typically they go hand in hand. And you don't want to deal with the hassle of managing the infrastructure, both for the storage of that data, as well as the compute side for actually doing that training. And so instead, what you can do is you can just take your existing TensorFlow code that hopefully you've tested out locally on like a smaller subset of your data, and it's working and things like that. So you push that up to the cloud, you package that up into a Python package, and you use CloudML engine to run your TensorFlow code for you. And what it does is it basically will provision all the virtual machines that it will run it on, network them together, and install TensorFlow and whatever packages it needs, and then push all your training data through that and run the training. At the end of your training, you're going to want to export your model because I touched on briefly, we touched on the whole notion of training and prediction, how important the other side is, right? The whole point of all this training is to answer questions. It's to do something with this model, not just to train with a good accuracy and say, that's it. So to then do the predictions, we want to deploy our model to kind of production in some form. And ML Engine helps with that as well. It has a whole prediction service. And what you can do is you can literally take the exported model from TensorFlow, which, if you do it in the cloud, it's just a couple of files that sit in a folder. You just point prediction service at those files, give your model a name just as a text, just label it, and you're basically done. You end up with an auto-scaling REST API that can handle just torrents of predictions. And not only does it scale up automatically for you, it also scales down all the way to 0 if there's no one calling it. And so, in a lot of ways, I see that side, the prediction side, as being like the real, awesome feature of this, because once you're done doing your training, you've already wrangled all your data, you spent all this time and energy writing the code. Now you have to go figure out how to deploy the service to production and make sure it's secure, make sure you have a good API, make sure all these things that it's just I just want to get back to my data and tune my model some more. So having a really simple way to deploy a model to production is a really awesome kind of feature of ML Engine. And with these exported models, I'll also add that you can do the training locally. So say you have a cluster of machines and you run your TensorFlow code, you do your training, and then you export your model. So you just got some files on your hard drive. You can upload those files to cloud storage, and at that point, you can pick up where in the middle of those steps where you just point the prediction service at those files, and you have an auto-scaling API. And so you don't necessarily have to do training and prediction in the cloud. You can do one or both. You can do one or the other or both.
Okay. Yeah, I wish we could go deeper on that, and we should definitely do another show in the near future because we didn't cover nearly all the stuff I wanted to cover with you, because some of your talks, you go into detail and how to deploy this stuff and some of the other features that you could be doing with CloudML. So let's save that for another time and wrap it up here, since we did a really good job covering the model training and the basic CloudML deployment stuff. So thank you, Yufeng. Thanks for coming on the show.
Yeah, thanks a lot, Jeff. And I guess the only thing I'll add here is that, in terms of other resources and materials, recently I've been putting out a set of videos, a series called Cloud AI Adventures. And so that's a series that's available on YouTube on the Google Cloud YouTube channel. So if folks want to learn more about both like machine learning as well as CloudML and kind of just the entire data science ecosystem, the kind of subtitle of that show is to explore the art, science, and tools of machine learning. And so that's been really fun to kind of make and produce. And so I hope folks, can get a lot out of that.
That sounds like great content for me to watch. And, let's get something on the calendar for another show, and I'll consume some of that content before we do that next show.
Awesome. Sounds good. Thanks so much for the opportunity. It's been really fun chatting with you.
Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar, SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Writely is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast. And you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR. softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily.
Wow!